Today we're learning about repeated games. So one application out of many would be if you have firms in competition. So when they compete today, they're not just competing today, they're also competing in the future in the next period. So repeated games compared to other games can give you stronger incentives to cooperate. That's because if someone does not cooperate in an early part of the game, you can try to punish them later on. If the game is played just once, there is no later on, so the idea doesn't work. However, as we'll see, repetition is not always sufficient to induce cooperation. So let's analyze the repeated Prisoner's Dilemma game that you guys just played as one of your in-class games. So we had this setup. We had our two prisoners. You can either confess or don't confess. And each time the payoffs looked like the following. So usual story, if you both don't confess, you'll get convicted for a minor crime. If you both do confess, you get convicted for the bigger thing you guys did. If one confesses and the other doesn't, the one who confessed goes free, and the one who stayed silent gets thrown in prison for 20 years. So that was our setup. So repeated games are a special case of sequential games. So each repetition is like another turn in a sequential game setup. And we all know what's our favorite tool for analyzing sequential games. That's rollback, also called subgame perfect Nash equilibria. So we're going to start at the very end of the game, the third repetition, figure out what do the players do there, and then work our way towards the front. So we're at the last repetition. Now the game is being played effectively just once. We already know what happens when the Prisoner's Dilemma is played just once. That's both players confess. Confess is a dominant strategy. So this is still consistent with our story we had earlier. We said that if you don't cooperate, you could be punished in later rounds. Well, at the end of the game, there are no more later rounds, so those incentives to cooperate go away. So there's not going to be cooperation in the final round. We can be assured of that. Hang on just a moment. I gotta get some more paper. All right, there we go. We have more paper. So once we figure out what happens in round 3, let's go back to look at round 2. So we established that no matter what happens, both players are going to confess in round 3. So if I cooperate in round 2, I'm not going to be rewarded. I know they're going to confess in round 3. Similarly, if I don't cooperate in round 2, I know I'm not going to be punished because both players confess are going to happen anyways, regardless of what I do. So there's still no incentive to cooperate, even in round 2. So that means they're both going to confess in round 2 as well. So now we go back to the very beginning of the game. And you'll probably see the pattern by now. So we already know that in round 3, both players are going to confess no matter what. There are no further repetitions beyond round 3, so no incentive to cooperate there. However, if we know that players will definitely not cooperate in round 3, that's going to kill the incentives to cooperate in round 2. We just established that. So if both players are not going to cooperate in rounds 2 or 3, regardless of what happens, then there's still no incentive to cooperate in round 1. So again, both players confess. So we see in this case, adding repetition is not enough to induce cooperation, at least in theory. So while repetition can make cooperation more likely, as we can see, it doesn't always guarantee cooperation. You still get uncooperative play even in the face of repetition in some circumstances. So there's actually a more general result here. It's not just true for the prisoner's dilemma. The more general conclusion is that whenever you have a unique Nash equilibrium, then adding a finite number of repetitions is not going to cause you to deviate from that. There's just one Nash equilibrium in the one shot game, the game is played once, then you'll keep playing at one Nash equilibrium over and over and over again if the game is repeated a finite number of times. so-called the one-shot game, the game that's being played just once. So you can play the Prisoner's Dilemma 10,000 times, and every time they're going to confess. That's what our equilibrium is going to be. So that's what happens if you have a unique Nash equilibrium. I'm going to show some foresight today. I'll stop the video right here before we run out of space and have a second shorter video instead of having the video end abruptly when my phone runs out of memory. So come back for episode 2.